EC 201, lecture 16. So far we have figured out ways of biasing a transistor so as to keep the operating point, which in other words is simply the quiescent current through the drain of the transistor, to be quite independent of the threshold of the device, and this was accomplished by the use of negative feedback. Okay, I think now the time is ripe to basically sit and study this, what this negative feedback is all about in a little more detail than we are used to. And today we will also understand the rules that you often use blindly, I guess, during your previous classes, that when you have an op-amp, the two input voltages are equal, okay, and no current flows into the input of the op-amp and all that. I mean, are you guys familiar with this stuff? We'll try and understand why those rules make sense, okay, and when those rules make sense, so that you can be on a fairly sound theoretical footing. If I wanted to draw the block diagram of a negative feedback system, what would I do? There is certainly a reference quantity. You are comparing some output quantity with the reference, and what did we say was comparison? Subtraction. So you have some kind of arrangement which takes these two quantities and subtracts them, and you have some kind of mechanism which makes sure that, I mean, this you can think of this box here as some kind of big brother who basically makes sure that the output does what is required. Okay, so the moment, so this guy is like, a gun for hire type chap who will not brook any nonsense, and the moment this error, okay, so ideally you want Q naught to be equal to Q ref, okay. So if there is any error between the reference and the output, then this is called the forward block, and the forward block makes sure that it gets very upset when there is a finite error and kicks this output in such a direction so as to make the error ideally zero, but we'll see what the forward block, what the properties of the forward block must be in order that the error must be zero. Alright. In many cases, for example, what is compared is not just the output, but some function of the output. There is nothing. So instead of comparing the output directly, you can compare some fraction of the output. For example, if this is QO, this quantity is F times Q output. In general, none of these quantities, Q ref or QO, none of these need to be electrical quantities. For example, Q ref can be a mechanical quantity like pressure, for example. QO can be position, and so on. So it's not necessary that Q ref and QO can be, so Q ref and QO can be different quantities. Example, voltage, current, etc. However, can you make any comment on Q ref and F times QO? It doesn't make any sense to add apples with oranges, right? So if you have apples, you must add them with apples. Q ref and F times QO, alright, which is often called the fed back quantity. This is the reference quantity. The fed back quantity and the reference quantity better be the same. It doesn't make sense to add voltage with current. The dimensions of the gain of the forward block, for example, are going to be the ratio of the output quantity, the units of the output quantity divided by the units of the reference quantity. Does this all make sense? And since we are now dealing with electrical circuits, we will make life easy, but all these quantities will basically be either voltage or current. In which case, if I redraw this in the electrical domain, for example, this is the forward amplifier. Let's assume that this has got a gain. Alright. This is the output voltage. A portion of the output voltage is fed back, so that this fed back voltage is F times V out. So the fed back quantity is compared with the reference quantity. So, and we know that comparison basically means subtraction. So we have to have some way of subtracting F times V out from Vref. The error voltage is that which remains after the subtraction, and that goes and excites the forward amplifier. In general, I mean, nothing is illegal when if A and F become nonlinear blocks. Okay, life becomes a lot more difficult to when nonlinearity is involved. So we will at present simply restrict ourselves to situations where everything is nice and linear. So let's try and find the output in terms of the. How do you figure out what the output is? You write the equation. So VE, the error voltage, is Vref minus F times V out, and V out is A times V. Okay, and it's since these are two linear equations, it's quite straightforward to solve. In practice, as I keep saying, things are nonlinear. When things are nonlinear, analytical stuff is often confusing to most people, whereas a picture or a graph is gives you a lot more intuition. So I will try and solve these two trivial equations graphically. How will I solve the equations? Okay, so first job is to draw a graph. Okay, so and once you draw a graph, the first thing to do is label the axes. So what are the axes I would like to use? Pardon, VE on the x-axis and V out on the y-axis. So if I had to plot V out as A times VE, it's simply a straight line through the origin. What about this equation? Thankfully, this is also a straight line. So what is the intercept on the y-axis? It's Vref by. What is the slope? Is it positive or negative? Slope is negative, and what is the slope? Minus 1 over f. So it better be a straight line. So the solution that we are looking for is basically the point of intersection of these two lines, which happens to be this guy here. Can somebody help me find what this is? So I need to basically be able to figure out both the input, that is VE. What does this correspond to? This is nothing but Vref by 1 plus AF. Okay. And what is this? If this is Vref by 1 plus AF, this is on this point here lies on this straight line. So it's the output must be, so this must be Vref times A divided by 1 plus AF. Now let me see what happens when I increase the slope of A. So what happens to the point of intersection? This becomes the point of intersection. And what happens to the output? What's happening to the error? As the gain of the forward amplifier, which is A, increases, graphically what do you see? The error VE decreases, and what do you think happens to the output? Okay, output increases, but what happens if I keep increasing the slope, making the slope A higher and higher and higher and higher? What happens to the output? And specifically, as A tends to infinity, VE tends to 0, and V out tends to Vref by F. Quite straightforward. Okay. So, couple of observations. If A becomes very, very large, does the absolute value of A matter? Whether, let me take two cases. So, what do you see here? The slope of the forward amplifier here is much smaller than the slope of the second forward amplifier. These are two situations where I have two different amplifiers in the forward path, and you can see that the gains of the two are very, very different. The slope of this curve is much higher than the slope of this curve. However, you see that in spite of there being a huge difference in the slopes, the output still remains very close to V ref by F. So is that apparent, or it's no, not clear. Let me just plot the first quadrant. This is V ref by F. This was 1A. This was A1. Let me draw something else which has a larger slope, and the third one which has even larger slope. You have to imagine that the slopes are now tending to, all the three are tending to infinity, but there is, one is still many times the other. And you can see that as the gain of the forward amplifier keeps increasing, the absolute value of the gain doesn't really matter. The output will be very, very close to V ref by F. You can see that in the math also. So V out is basically A V ref divided by 1 plus AF, which I can write as 1 over F times AF by 1 plus AF. As A tends to infinity, V out tends to 1 over F times V ref. Further, if this quantity AF is very, very large, if AF is much greater than 1, then V out by V ref is approximately 1 over F. So if this quantity AF is very, very large, whether it is 100,000 or 10,000, it hardly matters. So for example, if AF was say 1000, then V out by V ref will be equal to 1 over F times 1000 by 1001. On the other hand, if AF was 10,000, it would be 1 by F times 10,000 by 10,001. So if F remained the same, the only way of changing AF is to change A. So we see from this this example that even though A has changed by a factor of 10, which is a 1000% increase in A, you can see that the input to output gain has changed by some ridiculously small factor. Okay, it was F times 0.999 before, and now it is F times 0.9999. Okay, so the relative change in the gain from input to output of the feedback system has not changed at all, or it's just changed very, very little. In other words, so this is A, this is F, this is V ref, subtraction, this is V out. Okay. So this in feedback parlance is called the forward path, is called the feedback path, and V out by V ref is called the closed loop gain. So what do we notice? The closed loop gain is very, very insensitive to A, as long as this quantity AF is much larger than 1. In other words, the input-output properties of a feedback system only depend on what? What is the closed loop gain? If AF is much larger than 1, what is the closed loop gain? It's 1 by F. Okay, so the closed loop gain, this becomes equal to 1 over F approximately, if AF is very large. In other words, the performance of the feedback system is dependent on the, let me say, closed loop performance of the feedback system is dependent on the feedback paths, as long as AF is much greater than 1. If you wanted to get closed loop gain, what must F be? Closed loop gain, F must be smaller than, alright. I mean, in other words, see, this A is, yesterday we were talking about a legal analogy. A is basically, whenever you do something, you always think about the consequences. At least I hope you do. So, if you know that the legal system is very strong, that corresponds basically to a large forward amplifier gain A, because you know that even a small difference between what is expected of you and what you actually are can be very costly. You understand? So in other words, a strong forward amplifier, or a forward amplifier with a very large forward gain A, will tolerate very little nonsense between the feedback path and the reference paths. Another way of looking at it is that if A tends to infinity, if the output has to be finite, if A is infinite, if this chap has to be finite, what must happen? The error must be 0. If the error is 0, it means what? Vref must be exactly equal to F times V out, which basically means that V out by Vref is nothing but 1 over F. Does it make sense? And why is this called negative feedback? At time t equal to 0, V out is exactly equal to Vref by F. A is infinite. Okay. So, what do you think will happen if I, for some arbitrary reason, I perturb V out by a little bit? Let's say V out goes up a little bit. If V out goes up from this value of Vref by F by a little bit, then what do you think will happen to how will the feedback system react? Vref still remains the same. The output has gone, for some reason, been perturbed, and it has become something more than Vref by F. Since the output is more than Vref by F, the forward path is being excited by Vref minus the output. So what happens to the error? Error goes negative, and what does the amplifier do? It tries to pull this output in the opposite direction. Okay? And it's not just trying to pull the output in an opposite direction, it administers a really hard kick in the opposite direction. The loop, the output knows that if it is up to any mischief, it will get it really hard from the forward amplifier. So the output stays put at Vref by F. Does it make sense? Now if you have a loop, one thing you must understand is that light doesn't come in block diagrams. You will not have, for example, in an electronic circuit, a black box which is saying Vref minus F times VO. You will not have a black box with a label on it called forward amplifier. For example, in the bias arrangements that we saw, could kind of dissect things and then interpret one as the, as subtraction and one as the forward amplifier and so on. It takes some doing, and when you just look at a circuit, it becomes very difficult in a lot of cases to explicitly draw out the summation, the forward amplifier and the feedback part. How do we know if there is negative feedback. The test for negative feedback operation is the following. One way you could think of it is to break the loop at one point and yank one end of the loop up one way or the other. Let's say I pull this end of the loop up. If this moves up, what happens to this part? What happens to the output of the feedback path here? If this goes up, this also goes up. If this goes up, what happens to the error? This goes down. If this goes down, what happens to the output of the forward path? Output goes down. Okay? So what do we see? Any attempt to pull one end of the loop up is met by a massive restoring force in the opposite direction. So this is the classic test for negative feedback. So you break the loop, apply a stimulus at one end, go through the loop and see what comes back, and if it is negative feedback, then the output of the system of the loop will be in the opposite direction of the excitation you put in. If I yank this up by delta V, what is the numerical value of the quantity here? F delta V. Let's assume Vref is 0. What happens? The error becomes minus F delta V. So what happens to the quantity here? Minus A F delta V. So if you cut open the loop and you excite the loop with delta V, what comes back is the opposite sign of what you put in and AF delta. This quantity kept appearing in all our equations, this AF. And what is this? As we saw, it is the gain that one gets around the loop when you break it. Okay, if you break open the loop, apply a stimulus, at one end, what you get out at the other end is AF times delta V in the opposite direction. Okay, so it seems quite apt to call this AF is loosely called the loop gain, which is the gain you get by going around the loop. The closed loop gain can be expressed as 1 over F, where F is the gain of the feedback path times this quantity loop gain divided by loop gain plus 1. AF by AF plus 1, and AF is the loop gain. So the closed loop gain is 1 over F times the loop gain divided by the loop gain plus 1, and as the loop gain tends to infinity, the closed loop gain tends to 1 over F. We see that the closed loop gain of an amplifier, when you have it designed using negative feedback, is only dependent on the feedback paths. If you want a closed loop gain, then the feedback path must have a loss. Or if you want an amplifier, the feedback element must be an attenuator. And attenuators are very easy to make. You take a resistor, put two resistors in series, and you get a voltage attenuator. If you put two resistors in parallel, you get a current attenuator. If you make a potential divider with a gain of 1 by 10, then if you put it in a negative feedback loop around an amplifier with a very, very large gain, then the closed loop gain will be 10 as long as this large gain is very, very large, where very, very large means that this number A times F is much, much greater than 1. Does it make sense? And why is, why do we have to be so excited about it? The reason is that, as you've already seen, you need active devices. Okay, you can only get incremental gain, and that involves transistors and so on. So it is possible to get a fair amount of gain. You've seen, GMR, the gain is GMR. If you wanted to get more gain, you can put many such stages in cascade and get, as in principle, as large a gain as you want. So you can get very large amount of gain, but this gain depends on GM, okay, which in turn depends on mu and Cox and all this kind of stuff, which in turn depends on ambient temperature in the way the transistors are made. So it is possible to get a large gain using active devices, but it is extremely difficult to get a gain which is constant with environmental factors and aging and so on. If you only used an open loop system without feedback, then the gain would be, as you've already seen, is of the form GM-RL parallel RL1 and all this other stuff. And you find that this gain depends on GM, which depends on a whole bunch of factors like doping, concentrations and manufacturing variations of the transistor and so on. But that need not bother us now, because we have found a way in which, if you use transistors and don't worry about the fact that the gain keeps changing. In fact, as you've seen in a simple example, even if the gain changes by a factor of 10, it doesn't matter as long as the gain is large enough. The only thing we need to be concerned about is how constant with temperature is this feedback factor, the gain of the feedback block, which is X. Okay. Since we know that the performance of the closed loop system is dependent on the properties of the feedback network, we got to make sure that the attenuation of the feedback network doesn't vary all over the place, and that is very straightforward to ensure. Why? So as we saw before, if you take two resistors in series, okay, if you make, the feedback ratio F, okay, can be very easily be made to be it's a dimensionless quantity in this case. So it's very easy to make it a function of, or can be made to be a ratio of like quantities. So it's very easy and straightforward to get an attenuator whose properties are independent of temperature. And on an IC especially, if you make two identical resistors, even though the resistors may drift off from their absolute values, the ratio of resistors remains very, very stable. With, even though R1 and R2 vary, R1 by R1 plus R2 can be very, very stable. You understand? So now we have basically divorced the problem of making a gain which is, stable with process and temperature and manufacturing variations into two separate problems. One, which is to design the forward amplifier with as large a gain as possible, and the variations in the gain don't bother you anymore, because the properties of the closed loop system are very, very insensitive to the properties of the forward amplifier, as long as the gain of the forward amplifier is sufficiently large. Okay? And the second part of the problem is to make an attenuator whose properties remain sufficiently stable with process and temperature, and that is quite straightforward, as we have discussed. So now coming back to the negative feedback example, as long as the gain of the forward amplifier A becomes infinite, what can you say? Okay, so the rule is the following, which is, if A tends to infinity, we saw that if A tends to infinity, or if the gain of the forward amplifier becomes larger and larger and larger, the error quantity simply becomes 0. Turning this upside down, if you knew that you have a negative feedback system, this is some network, you don't even know what is inside, but all that you know is that you have a negative feedback system, Vref, Vout, and this was infinity. Then what can you say about this chap here? The forward gain is infinity, and you know that you have negative feedback. And what do I understand when I say negative feedback? How would I figure out? This is obviously a very complicated network. How would I go about figuring out if there is negative feedback here or not? I will break the loop anywhere. For example, here, excite this end of the loop with some delta V, go around the loop and see what comes back here. If what comes back here is in the opposite direction, then I know that there is negative feedback. So if there is negative feedback, then we know that the error voltage at the input of the forward amplifier must be 0. So in other words, the negative feedback loop is one where if there is a disturbance in the loop will react in a manner so as to cancel out the disturbance. The opposite situation occurs when there is positive feedback. Okay, this is analogous to a situation where your GPA is 4 and then your parents get you a car because the difference is 6, so that's probably a good thing. Okay, and then you're now motivated to actually try and lower your GPA so that hopefully you get a better present the next time. You understand? That's an example of a positive feedback loop. And you can see what happens when you have a positive feedback loop. What do you think happens? This is where a graph helps again. So when we had negative feedback, this was the line corresponding to the feedback equation, which is V ref by F, and the slope of this is minus 1 by F. This was the situation for negative feedback. Okay, and you know that in real world applications, the voltage of any amplifier cannot go to infinity. So in practice, there will be an upper limit to the output voltage, there will be a lower limit to the output voltage. If you screwed up the sign of the amplifier for some reason, inadvertently, then what happens? You have a situation where you have something like this, and this is the line that this is V ref by F. The slope of this line is minus 1 by F. For negative feedback, this was the solution to the two equations. Okay? Does everybody follow? So for positive feedback, by the same token, what are the solutions? There are two, or there's some solution outside the blackboard. So there is one solution here. One point of intersection there is one point of intersection there, and there is another point of intersection where this guy intersects this chap. Okay? So when you have a practical positive feedback system, it turns out that you will have 3 potential solutions, and this is the solution close to V ref by F. It turns out that solution is an unstable solution, and I won't go into the details of why the solution is unstable, but you can think of it in this way. Let's say the system is settled at this point, and there is a small disturbance in the system. In negative feedback, when there is a small disturbance, the feedback loop tries to restore the original operating point, because if there is a disturbance, the feedback loop will react in a way as to eliminate the disturbance, whereas in a positive feedback system, it will try and enhance the disturbance. Okay? So if there is a small perturbation, the output will, since what comes back once you go through the loop is much larger than the disturbance, it will be plus AF times the disturbance, and it is in the same direction, so it will push it even higher and higher and higher, and eventually until it either reaches this operating point or the other operating point beyond the board. Does that make sense? So instead of, if you committed a crime, instead of going to jail, if they gave you an award, then what would happen? Everybody would be slitting each other's throats all the time so as to get more and more rewards, isn't it? So that's an example of a positive feedback system.